So we are now recording, and there's still 13 of you. I think we got about 50% of all the class here. So if you know any of your friends who wants to join today's class and saw the announcement saying we'll start at 10:30 and forgot to come back, please tell them you should come back. Sorry again about having to postpone the class for a half an hour. As I said in the in on Canvas, basically I'm pretty sure we'll finish before 2 p.m. because these are basically the only topic left for this class. And then I'm going to be on Discord afterward. And if you have not catch me in the beginning, I told you guys that for the exam, oh, there's an open house. I see. That's why. Okay. So is there like a specific set of time that you're supposed to go and help out your friends on the open house? Or is it that basically, okay, if that's the case, so for the content of the class, I can basically power through without a break, and I'm pretty sure we'll finish by noon because a lot of these things are stuff that you've seen in other classes before. We'll kind of like formalize it today. So let's begin the class now. So today we will talk about what is the streams and what's the lazy evaluation, right? How many of you have heard about stream in other languages? How many of you deal with stream before? Anyone have seen that before? Yes, no? Only on Stack Overflow. Okay, good. All right, Steam Reader. Yes. Okay, so these are exact same concepts. Whenever we talk about streams, that's like a proper definition about it. But before we go to stream, let's talk also about lazy evaluation. So let me ask you this question, right? Once I give you an assignment, when do you actually start working on it? So usually my assignment for this class is about 2 to 3 weeks long, right? So let's say I give you an assignment right now and it's due in the next 2 weeks. What do you usually do? I'm not saying to critique you or anything. I do this too. About 2 days before it's due or 2 days, a night before the due date. Okay, that's like what I did, right? So what I typically do is I'll read the assignment and I'll try to figure out, okay, do I have to start now because it looks hard? Or can I start it later, right? A night before the due date or 2 nights before the due date. My recommendation is like maybe 3 or 4 days before the due date because sometimes there'll be like small surprise going in. You thought it's easy, but then it's like, oh crap, it's not that easy as I thought it would be. So this is the same thing as computer. Well, not we, I'm not a computer. Yes. Computer can also procrastinate. And that's a good thing, right? So why? What's the benefit of starting your homework late? Can someone tell me what's the benefit of starting things late? Enjoy life. Yes. So basically you can spend your time doing something else, right? Not doing anything. Relax, right? And the same goes with computer. Think about it this way. What has to happen? Let's say you need to compute something, right? What is the power source of your computer? How do you power it up? You plug it, you plug your computer on, right? You power it on through electricity, right? So it means that it burns power. If I say, okay, I can relax and not do anything, not burning my energy on computing certain things, and I'll do it when I need to do it, right? It's not like I procrastinate to the point I miss the deadline. That's bad, right? As long as I can ensure if I need something, I will evaluate it. But if I don't need it, I'll skip and not do it, right? Is that a way you should approach life to some extent. Yeah, I mean, why not, right? As long as you don't miss your deadline, as long as you can enjoy life, work-life balance is a good thing, right? No matter what I do in life, which sounds make basically I tend to make my life a little bit more miserable than I need to by signing on many things. But at the end of the day, you want to enjoy life, right? So computer again, it consume power. Whenever you need to compute something, it actually burn energy, right? And I assume your generation, including my generation, we all have to be careful about how much energy I consume, right? Those greenhouse gases and everything. Yeah, so it's good not to consume too much energy. So evaluation, we can also evaluate things lazily, right? And this typically lead to more efficiency. You spend less time on your assignments, more time panicking right before it's due date. So, how many people start their assignment one day before it's due, figure out it's harder than you expected, and you panic? Yes, no. That's okay. Great. We have the same life. Yeah, I do too. Uh, so but at the end of the day, it's lead to more efficiency. Like when you panic, or if you panic in a good way, in the sense that your adrenaline jump up and you work faster, right? But still, if you are still sane in the sense you can still think properly, then you work faster. That leads to more efficiency. Uh, we will use stream as an example of how to lazily do things, but let's first define what is a stream. So a stream is a flow of data, right? That's basically the definition. You have data that keep coming in, that keeps coming. Definition, proper definition is you have infinite, that's a keyword, infinite, typically way too large for your memory, an infinite sequence of data. How many of you heard about this terminology called big data or big data analytics or well, I think people still use the word big data. So have you heard about that term? And like whenever the government say industry 4.0, you need to deal with big data. Anyone can tell me what does big data really mean? Oh, actually, let me tell you what big data really mean. So if you think about how the computer, yeah, basically it means the data is big, but big is vague, right? So basically, if you want to pinpoint this a little bit more, it's too big for your DRAM. But whenever you buy a computer, one of the things that you consider is how much memory should I buy, right? The more memory you have, the more cost your machine is, right? For example, you look at the new MacBook, which is an so how many of you seen that new announcement from Apple with their own M1 chip a couple of days ago, actually? They have a new MacBook with a new chip. That chip seems awesome from the point of view as an architect. For me, it's like that chip seems interesting, and it should. When I look at the fact that now you can power your laptop for like 15 hours, that's crazy. You don't get that much performance in one generation typically. So you somehow it's faster, somehow it's actually more power efficient. And from their design, I kind of know why, but it's not the context for this class. If you look at that MacBook, one of the things you saw is it can support 8 to 16 gigabyte of memory, right? 8 to 16. And it also contains this processor that do machine learning. So for those of you who take machine learning class, how big is your data that you're training? I'm trying to gauge where you are when in the deep learning world. 2 gigabyte right now. So that's not big. So if you are looking at real data that are running on the GPU side, we are talking about tens of gigabytes and more. Basically, the concepts behind deep learning and why to some extent it's really good and why it's really popular is the more data you throw in, the more accuracy you get. So if you have data, you can throw in those data and you get better at predicting. The downside is your memory is limited, right? This means that the data is too big for your DRAM. That means it can be categorized as one of the big data application. Why do we care about big data application? When you it takes forever to train if you fail. Yeah, that too. Basically, it train forever. Big data means that the time it takes to reach your data, because it's way too big, is a lot bigger than your main memory. The time it takes to reach your data can be up to how long it takes to reach the files on your hard drive, right? And if you look at how fast your hard drive is compared to your DRAM, you're looking at about 10,000 times slower. So when you write a program, let's say you do Fibonacci and your input somehow is way too big for your DRAM. What will you feel if your Fibonacci function turns out to be about 10,000 times slower? You cried in the inside, right? So what happened to my program? How many of you open too many Chrome tabs to the point your machine freeze? Out of curiosity, also, how many tabs do you have if that happens? So I don't go that far, personally. So anyone been like using Chrome and never close their actual windows and keep having tabs on to the point that you have like 10, 20, 30 tabs. And at some point your machine, okay, these are interesting number. You know someone. I'm waiting for in suspense for the next sentence. You know some, but basically never close any tab. Okay, that's way too interesting. Don't try not to do that. The reason behind it is if you don't close the windows, it will never. I think Chrome might put some thread in the background, but it might not actually kill some of the threads that you're not going to use it again. But if you have hundreds of tabs on, you might feel that hey, your computer gets slower, right? Because some of the data is actually not in your memory anymore. It's on your disk. So that's part of like what it means to be talking about big data, right? And it's not a new problem. The problem of having memory too small comparing to the data you're reading is classic. It's been there for forever. Since the dawn of computer, you never ever have enough memory. But Stream comes to your rescue. So come back to our topic. When your data becomes too big and you only can access the memory to get your data, Stream is your solution. You are basically reading your disk, right? The disk as basically that magnetic disk that you see, you are basically go through them one bit at a time, one bit at a time. The head, the spin, right? The spin around, those are reading the bits. And that go through the Stream interface, giving you this infinite amount of data. Why are these interesting? As I said, many real-world applications have to utilize Stream. Anything that connects to the network, they are Stream. Anything connect to the hard drive, they are Stream. Anything that connect to I/O, what is I/O? Input and output, keyboard, mouse, or whatever, right? They are Stream. Why is my input on the mouse, right? The cursor that I have, right? Let's say I have the cursor that looks like this. I'm going to switch to laser pointer. And let's say I'm moving my pointer around like this. So you see me moving the cursor around. These are basically series of input, right? These are series of input that the user might keep giving to you as in the program, right? So these are stream. These are all stream. Example of the more mathematical stream, sequence of prime, right? You start with 2, 3, 5, 7, 11, 13, 17, 19, right? Those are series and sequence of prime. And this can go up really, really far. Basically, this is infinitely large. You can also have things like digits that represent the value pi, right? 3.1415. I don't even know what's the next number. But these number will keep going, right? The packets that you receive on a LAN port that you listen to, basically whenever you have a boot up a computer, your network interface will listen to packets that come in and process it, right? For example, if you open a Chrome tab, open up YouTube, it will send the packet to the YouTube server. The YouTube server reply back with the video, basically with the data of the video that you need, you want to watch, right? And you don't know when will this video arrive, right? If your internet sucks, it might take 5 seconds. If your internet is really good, it will take less than 1 second, right? You don't know when the data will arrive. You don't know how long the data is going to be arriving. And these are essentially infinite sequence of data. Any questions so far? This is kind of like a proper definition of stream, infinite sequence of data. So once we have a stream, let's talk about how we can actually access a stream. So because we are going through both Scala and Rust right now, I'm gonna just have this like pseudo code that looks almost like Scala. So let's assume we define stream as a and double colon stream, right? What does this mean? A is a type. So basically it's a data type that comes in. What is this particular data type? We talk about the product type, sum type, and recursive type. What is this? Product type, sum type, and recursive type. Which one does stream fall in? Is it a product type? Does it look like a pair or a tuple? Is it a sum type? Does it look like an option? Or does it look like a list, which is a recursive type? What does it look like? It looks like a list. So basically, this is one of the recursive type, right? Because they are infinite sequence. What is the difference between stream and a list? Stream is infinite. A list has finite elements, right? So what does it mean? It means that stream doesn't have the base case. Recursive type usually have a base case. Stream never have a base case. So you keep going on and on and on and on, right? And in theory, when you have a list, right, you can do pattern matching to get the head and hopefully the tail list, right? So you can do H and T, right, to get the head and the tail list. What is the problem? As I said earlier, the stream is infinite. So I guess we can kind of cover the beginning of your stream, right? The first number of your prime number, the first number of the digit representing pi, which is 3, right? That would be the first base case. So we begin our stream with nil or nothing, followed by the first element, the second element, the infinite element. Where do we end? That's the problem. That's the second problem. By definition, is infinite, right? So what will happen if you need to evaluate a stream? It doesn't really terminate. There's no termination point. There's no base case, right? So let's first talk now. We talk about stream. Let's formalize one operator that has been our old friend for a long time. This is called the cons operator. That double colon that we have been using in Scala, that's called the cons operator. And because a list is a recursive type, you can keep appending things. So if you want to kind of like not merge, but like change the stream into something that looks like a list, basically just define a list that doesn't have the base case. Append, and append, you are going to basically have the stream of inputs. of certain data type, right? So this cons operation allows you to deal with the stream because it's basically extend stream and it works on stream. If you look at Scala, the cons operator, the link is here. It actually has more uses besides just sticking things after another. Okay, so if you click that link on the PDF, you'll see an actual API for the double colon operator. Like what else can it do? So basically that's for the cons operator. Any questions about this? This kind of like almost apply the same way we work with a list, right? Think about it this way. A stream is a list with no ending. So the problem with applying function fn, I don't have the enough room to put the two line for the title, basically applying a function to a stream. So let's say we want to apply a function f to our stream, right? Using a map. Anyone want to guess what can be the problem here? Can I map function f to our stream? So in theory, yes, we can apply function f to every single element of our stream. The problem is the map function is what we call eager operation. What is eager operation? I'll give one example. Vicky, you are one of the students who somehow loves to just read the assignment and do it right away, right? At least that's how you told me how you work on your assignments so far. So these are eager operations where if you are told these are the jobs that you should do, you kind of like do it right away. The problem with eager operation on stream is this. So stream is infinite. It means that somehow I need to apply this function forever, right? Will that terminate? So a map is an eager operation. So what will happen is when you apply a map, it will apply that function to every element right away. So what will happen if we do that? What will happen? It will never terminate. You are in an infinite loop, right? So there's no way to evaluate an entire stream because, as I said, map is eager operation, and this will never terminate. So the solution is, well, in this case, be lazy. Take one element at a time and don't evaluate the entire string. One example is, let's say, in life, right? You are going to, I mean, if you think about it this way, this sounds way more depressing than when I type this sentence out, I promise you. But a human, whenever you're born, you're gonna have basically infinite amount of work in life, right? That's why I said it sounds a lot more depressing than I intended to be. So what should your plan be? How should you tackle? Sorry, I'm not supposed to make it this dark. But if you think about it, right? You don't know when the next task that you are assigned to will be assigned to you. So tomorrow you might have more work to do. Something come up and you need to solve it, right? So what should your strategy be? You do one piece of work at a time, right? That's the reality of life. Right? So all right, sorry guys, I can't stop laughing at I guess my life. So yeah, because things are going to keep coming at you, right? The way you should strategize and live your life is, well, you have jobs coming in. One strategy is earliest deadline first. You're gonna keep working on your job, right? And do one thing at a time. Do it whenever you need it, right? So I guess that's how you can be lazy in a sense that, well, there'll be infinite amount of work, some amount of work that comes in the future. There's no way you can prepare for that. So just do whatever you assign to right now. Right? Okay, that sounds a little bit less dark. Basically, at any point in time, you'll be assigned a finite number of tasks. You should evaluate those tasks don't worry about the possible future work that would come in the future. That's how you can evaluate things lazily. Okay, that less dark? I hope it is. Yeah, it's like game updates, right? Yes, you release the base game and you can play it now, right? So I think a lot of games these days that you can download like a non-HD version first, and then you can start playing. And then while you're playing, the games actually keep downloading the HD texture and everything. Uh oh, you mean the company that updates online game? Yeah, I guess that also applies here in the console. So to put those of you who don't play online games, uh, a lot of these company, when they are profiting, they'll keep updating their games and making things interesting. But at some point, people will get bored, so they're not updated anymore. So it's kind of like that. But it's a little bit more properly defined, formally defined in the context of programming, I guess. So lazily evaluate basically means that you are going to evaluate a function. By evaluate, I mean the first lecture evaluation, right? You have a definition and how you would evaluate that definition into a value. You do it lazily. So the naive solution is, yeah, you have certain amount of work. You are told to do this amount of work. You just evaluate just up to where you need to be, right? For example, if I tell you, get me 5 digits of the pi number, I'm going to give you 3.1415, right? The first 10 prime, I'm going to give you 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. What's the downside here? What if I say I want now 20 primes? I would have to repeat the same work, right? I'm gonna go check, okay, it's 2 prime, yes, 2. It's 3 prime, yes, 3. It's 5 prime, yes, 5. So you basically do 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, blah, 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 right? Solution here. So the problem, do anyone have any question about the main problem here? Basically, every time I ask you to do the certain things you have to do, you have to repeat the entire process, and that's not efficient. It's the same as, let's say I say, okay, assignment 1 is A, B, C, and D. Assignment 2 will follow up from assignment 1. Once you have all the code, then you build something on top of it. But my requirement is you have to redo assignment 1 again. You cannot reuse your code. What will you do to me? You basically will murder me right? Because basically you have done the work already. Why can't I reuse my code, right? So that's the downside of this naive solution. If you compute the first 10 prime already, store them, basically use memoization. How many of you never heard about memoization so that I can tell you what is memoization? Otherwise, I'm going to skip. Anyone want to vote yes on going through memoization again? Let's type yes quickly right now. It doesn't have to be to everyone. You can briefly. Okay, sure. All right. So in algorithm, right? One of the common algorithm that we can use as a programmer is called dynamic programming. So what does it mean for something to be dynamic? It means that it's gonna keep changing, right? And you will basically adapt to the changes, right? It's kind of like the reverse, the opposite of static. In dynamic programming, the key techniques that it's using is called memoization, right? And a prime example of memoization is, let's say I want to compute Fibonacci, right? So what is Fibonacci? Fibonacci is f of n equal f of n minus 1 plus f of n minus 2, right? Which is the same thing as f of n if you break down f of n minus 1. Why is it not memorized? I don't know. Actually, that's a great question. Is that a proper English word? For those of you who know memorization really well, can you kind of like help me check? I'm now curious about that. Basically, f of n minus 1 is breaking down to f of n minus 2 plus f of n minus 3, right? Plus f of n minus 2 is basically f of n minus 3 plus f of n minus 4, which is equal to f of n minus 3 because I'm breaking down f of n minus 2, right? Plus f of n minus 4 plus f of n minus 3 is basically f of n minus 4 plus f of n minus 5. F of n minus 3 again is f of n minus 4 plus f of n minus 5 plus f of n minus 5 plus f of n minus 6. And I'm hoping I'm not doing any mistakes here. Question is, if you look at this line, how many of the f of n minus 4 I have to do? 3. And then I also have to do 3 of the f of n minus 5, right? Memoization basically says this. There are so many repeated function calls, right? So once you finish computing f of n minus 3, store them. Oops, I did not realize this is a highlighter. That's why it looks weird. Oh, it comes from memo, not memory. Memo, like memorandum. Okay, thank you. Thanks a lot. I learned new things today. So basically, let's say I store this as temp. When I compute f of n minus 4, I will store this as temp 2, right? So when you have to compute f of n minus 2, this is basically temp plus temp 2. You don't have to call the same function again, right? If you have to do f of n minus 1, then let's say this is temp 3. This is going to be temp 3 plus temp, right? So is it like a dot zip? No. So the dot zip, the algorithm behind compression, it depends on what you do, right? The algorithm behind compression, one of the more classic compression algorithm is the other two algorithm that you would learn in algorithm class. One is called Huffman encoding. So for those of you who somehow took OPL, oh, no, you cannot have this cannot happen to you because basically the same iteration of this class, not last 2 semesters ago. The OPL class, I asked you to implement Huffman encoding during the midterm, which I deeply regret because it's too long. That's one of the compression algorithm. You build a tree, and each letter is a part of the tree. Basically, it's a leaf node of the tree. Another common algorithm is called LCW. I will not murder the guy's name, the inventor's name, by telling what's L and C and W stand for, because I would definitely murder that name. But you can look that up. And then these days, the other popular compression algorithm is called BZIP2. So BZIP2 is another really, really popular compression algorithm that's being used everywhere. So one tidbit, how many of you seen the .rar, RAR file? There was a time that was like really popular in Thailand, so stop using that. Use BZIP2 is better. So it's just as frank as that, like stop using the .rar file. Somehow it get like popular, I think 10 years ago in Thailand for some reason. And and I still see them now. So any question about memorization? These work for things like knapsack problem. If you are taking the algorithm class, the knapsack problem is one of the classic problems that requires dynamic programming. It generally has to do with having a table that store partial results. Over here, what you can do with Fibonacci is you build this array. This will be f of 0, and you write the value 1 1, f of 1 when you evaluate it, right? So once you know what is f of 2, you write in 2. When you want to compute f of 3, you just add the two numbers together, you get 3. You want to do f of 4, you add the two numbers together, you get 5. F of 5, you add the two last numbers together, now you get 8. F of 6, you add the last two numbers together, now you get 13, right? If you want to compute f of 7, you add just these two numbers together, you get 21. This way is faster. You don't have to recompute f of 3 10 times, right? So this is basically a technique called memoization and dynamic programming. Any questions so far? Yeah, basically keep the data you have computed so far. And that applies to lazy evaluation, right? Basically, you want to do the minimal amount of work as possible. And sometimes this is called call by need, right? So you have call by name, call by value. This is call by need. You look at all your tasks in life, just evaluate whenever you need them. Say we have two functions f of 1 and f of 2, and we want to evaluate f of 1 or f of 2. Do I have to care about f of 2 if f of 1 is true? My question is, if f of f1 is true, do I have to even evaluate f2? Nope, right? So you can skip f2. Call by need, I don't need to compute f2. I know this whole thing is going to be true, so I'm going to return true. Right? So that's exactly one of the example. So in Scala, you can use the lazy keyword. Literally, you can do this. Val temp is a big list. Lazy val temp2 is you are basically mapping a square function. If I get the number, I'm gonna multiply the number again. If it's 2, it will return 4. If it's 3, it's 3 multiplied by 3, 9. If it's 4, 4 multiplied by 4, 16. Then you do a lot of things here. It doesn't matter what you do, but it has nothing to do with temp2. And then at the end of the day, you say print temp2. My question is, for this example, when will temp2 get evaluated? I have two choices for you. The first choice is right here at line number 1 and right here at line number 2. So who thinks it's number 1? So when we call it as number 1, when we need it as number 2. So it's called by need. When you look at this code, right? When you look at this code, the first time that temp2 is needed is that print line temp2, right? So it means that we don't have to evaluate temp2 until you need to have that print line, right? Any questions so far? And remember, you can just say it's lazy, and it would do this in Scala. Why can this be useful? Let's say I have a code like this. If something print line temp2, else do something that has nothing to do with temp2. So it means that I can avoid, right? I can avoid printing, I can avoid evaluating temp2 if that if is false, right? If that becomes false, you go directly from here down to here. And you skip that temp2 print, so you don't have to evaluate temp2. Big profit, right? So any questions so far? Notice one thing, this is not a stream, right? So lazy evaluation, work on a stream, work on non-stream object as well, right? The key here is, unless I need it, lazy evaluation will not evaluate it. So we talk about memoization. In Scala, this is done by default. So Scala would do memoization by default, but some languages might not do it for you. So this is to actually apply memoization. There's a technique called the Jensen's device named after the inventor, or these days we call it Thunk. To be honest, I'm not sure why they call it Thunk. but but essentially this is it's a value that can means it's not yet evaluated. But when you call this, you are going to evaluate the results. So you get the value. And you evaluate Thunk lazily. Think of it as you're going to keep delaying this evaluation unless you need them. You need them. When you need them, you evaluate it. And the information that you need by Thunk is the arguments and the environment at the time of call. So you can evaluate it. Basically, these two are needed for your evaluation, right? And then when you evaluate it, the Thunk, so for Thunk, you can have two choices: unevaluated and evaluated. And let's say it evaluates to value v, so you return v right away. If it's unevaluated, and let's say this argument is A and the environment is B, so you're going to apply that function with A as an argument and B as the environment. Then you change your status to evaluated and store your results as V. Basically, a Thunk means that I'm gonna keep not evaluating until I need it. Once I need it, I'll apply evaluation. I'll store the output so that the next time I need it again, I don't have to apply the evaluation. I just return the output. To implement a Thunk, basically, let's say a function return type A, right? Generally, you need to capture the value if you have already calculated, right? So if it's already calculated, you return V. Otherwise, you are going to evaluate the expression, then store results as the value V. In Rust, there's also support Thunk, and here's the documentation. Basically, you can follow the documentation and lazily evaluate the expression. Right, so we cover both Rust and Scala. I'll show you an example of how to lazily evaluate things in Scala and Rust. In Rust, you have to be a little bit more explicit. You can use Thunk. In Scala, Thunk is applied by default. Now that we talk about lazy evaluation, I kind of want to wrap things up by comparing, right, the call by name convention and lazy evaluation. Why? Call by name also means that we are not going to evaluate until you need it, right? So at this point, you might be asking, so what is the difference between call by name and lazy evaluation? Call by name, as I said, is if you're evaluating expression when you need it. The downside is you still do repeated execution. You don't have this Thunk concept, right? So you don't store the evaluated value. You're gonna keep repeating the same evaluation over and over and over. The benefit of lazy evaluation is basically call by name plus memoization. Which typically is faster than call by name, right? It also means that if my call by name, if my lazy evaluation terminate, call by name will terminate. What would be the downside of lazy evaluation? So you're making a trade-off. You might be faster. What is your downside? Anyone want to take a guess what's the downside of having memoization? Not enough time. Yes, basically you ended up consuming a lot of memory, right? So the memory footprint of your program can blow up if the size of your stream is really big, right? So this means that it can be precious resources, especially with the big data application. Right? Your data is already too big for your memory, and if you use memorization, you're gonna consume memory again. Right? So you need to make this trade-off. You need to think about it. Like, should I use lazy evaluation? If so, how should I manage it? Should I free up some of the memory while you're doing memorization? Any question about lazy evaluation? Otherwise, because there's an open house today, there is an in-class exercise both in Scala. You will submit the code to compute all prime after n, but this time using lazy evaluation. Also with the all factorial up to n using lazy evaluation. For these function, n is the input. The output is going to be a list or a stream of, if it's all prime after n, it's going to be a stream. If it's all factorial up to n, that's a list. Make sure you have a way to test your code and submit your code on Canvas. And because again, as I said, I'm gonna kind of power through all the lecture, all the content so that you can go to the open house. The next concept that we talk about is iterator versus generator. The reason behind we want to talk about this is these two things are kind of like almost like a stream, and generator kind of picks up on the lazy evaluation of a stream. This is for program that's not functional programming like, which means that let's switch to Python for this part, right? So over here from this slide on to the last slide is all in Python. Is that okay? It's more iterative programming. It's not functional programming anymore. We will talk about how we can apply stream and lazy evaluation to different languages. So let's go back to 101. Yeah, exactly. So what is an iterator? Basically, it gives you an illusion that you have a linear sequence, right? It allows you to traverse collection of items, and it has a simple interface. Do you have the next thing? And if we have a next thing, give me the next thing. And the notion of iterator is similar across languages. This is one of the nice things about iterator. Whenever I talk about iterator, once you know how it works in, say, Python, you know how it works in C++ and Java. It's kind of like the same thing. So in Python, it's an object, right, which can be used with a for loop. There's a way to get a next thing, and there's a way to determine if there's no more elements. So if you want to create an iterator, you can say iter, right? You can use iter to create iterator. You get an object, and whenever you call next, you will get the next item. So if you do print next it, over here you first get 4, and then 1, and then 5, right? And then exception, because that's it, right? There's no next elements. So you can build an iterator from scratch, right? The requirement is, well, fundamentally, you need an internal index where I am so that I can give the next item, a way to keep track of the number of elements so you know how many items do you have. In the case of stream, this is infinite. You are going to keep having the next item. Two methods that you need is, well, return an iterator and return the current element. Then you move the index to the next element. Well, and in object-oriented programming, you will need a constructor, right? So how do you actually build it? Here's the constructor. When you init, you say, okay, index is 0, the size is n, iterator of size n. The method that return iteration, return self. A method that return the current element and then move on is you basically check if index is less than n, which is you can still iterate, right? You can return self.index, you increment the index, and you return that items. Otherwise, you stop iteration. Simple. So sample usage, you can use this for loop. Now you will print 1, 2, 3, 4, 5, right? you can use in conjunction with the list. Again, you will get the print of 1, 2, 3, 4. You can use iterator manually by first creating an iterator and print the overhead of running an iterator. So I'm going through this really quickly because it's just hopefully basic material you've seen before. I'm not going to bore you out. If I'm too fast, let me know. Basically, the overhead of the iterator is you need to keep track. That's first overhead. Keep track of where the iterator is. You need to write to certain specific method, right? This is a problem because you need to keep track of where iterator is, and you kind of need to keep track of all the elements, right? All the elements. What if you are dealing with stream? Generator comes to the rescue. Basically, iterator, if you have a stream, you kind of have to have the results of the evaluation. For generator, you don't. So the overview of the generator is this. Let's say you have the following expression, right? X squared for x in 3, 4, 1, 2, 5, 7. These expression produce a lot of values in the sequential order, right? You perform a map, right? You perform a map by squaring, not squaring, squaring these numbers inside the list. So comparing to the function, basically function produce one value, generator is generating series of value, right? It doesn't require multiple function calls, contain one or more yield statement. This is in Python. And when call, you return an iterator object, right? It implements the iter and next automatically. And once function yield, the control is paused. Basically, you stop running. The caller, the guy who called the function, resume. So if you go back to our example here, it will first compute 3 square, right? Basically, it will first compute 3 square and return. Then, if you say, I want to generate the next item, you are going to then compute 4 square, then return. One thing that you notice, you have not, right? You have not compute anything here. You lazily evaluated your function one by one by one by one, right? So that's the concept of generator and the yield statement. And stop iteration also rests automatically. That's more like making it easier to use. So you can use this along with code routine because you can hands off this internal state through a code routine. It's typically used in conjunction with generator, and you can pass the internal state in the background, right? A generator can pass internal state, which is where I am, where is the next item, right? Where I am and where's the next item in the background. So let's do some example of code routine. Let's say I define a function foo where you first print foo A and yield 3, foo B, yield 5, foo C, yield 2, and then print foo done. What's going to happen if I call this? I at first assign G to equal the foo function, right? The foo function. Then I'm going to print. I'm going to first print this line. Give me the pen, please. This line, followed by this line, followed by this line, followed by done, right? For all these 4 things. And then if you do h equal foo, you will then get the basically same usage, right? Where you print the list. Now it's basically doing the same thing. You cannot iterate through the list and print it, right? Which is good if you need to deal with infinite sequence, because let's say we want to assume the next prime is a coroutine. Finding the next prime is computationally expensive. we want to limit how many prime number that we should produce, right? If we want to produce up to n, just make sure you produce up to n. Generator can address this problem similar to lazy evaluation in Rust and Scala. So value are now yield back. Computation of the rest of your collection is paused. So you don't need to compute the actual infinite sequence of results. Generator allow you to keep producing the next element. So you yield basically. We will implement, so this is for Scala, right? So we will implement this as a part of an in-class exercise today where you will implement in Scala how you would get the prime after n as well as the factorial of 1 to n. And generator can also be used recursively like this. So let's say you have a nested list, right? So you can yield for each element in the list. These would do, let's say you have a list that's kind of like this. It's a list of list in here, right? What you do here is you want to return each element inside this inner list. You can then use generator by actually walking each list and return for each depth, right? Do the walking again inside each of the sublists inside the list. You can also pipeline where this work with stream. Right now you see that this is a stream, right? This is files, which is basically stream. So you can process the files, right? And just get certain lines in the files and print it out. So you can process this line column tree for the sales of log, which represent just the pizza column, and you want to figure out how many pizzas getting sold per hour. So you just only want to add column 3. You can use pipeline generator to just get to column 3, and that's it. You don't care about column 4, 5, 6, 7. You just go column 3 in that line and then process it. This code source is from this link. And basically that's it for the class today. We'll switch over to Discord for the in-class exercise as well as Q&A. As I promised, again, sorry, there's no break at all, but I want to make sure I give you time to basically switch over to the open house. And I hope you make it interesting for the potentially newcomers. Can you promise me that now that you want to go to help out in the open house? Okay, good. All right, so if you need to go help out, feel free to sign off. That's it for the lecture today. Next week is a holiday. So what I will do is I'm gonna record a YouTube video, post it, and say basically everyone can go and watch the video. There's a likelihood that I'm gonna have like a maybe one and more, basically between 1 to 2 hours review session for the exam. This is the end of the class for the material that will go to the final. Right, this is the end for the material that will go to the final exam. But because we still have time left, I'm gonna cover things like OpenMP and CUDA, which are two of the really popular parallel programming libraries. This allows you to write really fast program, really fast data parallel program, and really fast shared memory program through OpenMP and CUDA. Feel free to come with questions, as well as I'm gonna basically cover kind of like a quick review for all the material we have so far, so that you know these are the topics that might go into the final. That's it for the class today. As I said, I'm gonna switch over to Discord. and we'll do basically Q&A, anything over there. But any question before I stop sharing the screen? Any questions about the material we covered today? Okay, so feel free to investigate. That's it for the class today. When will the next Q&A be conducted? Actually, that's a great question. Let me consult my calendar. Because I believe next week I'm not allowed to do that on Thursday and Friday. So, I was about to say, I'm free on Wednesday, but no, not that. Uh, how about 11 to noon on Monday? Would that work for most people? Because another option is I'll start from the office hour, which is 10 on Monday to noon on Monday. Basically, I'm gonna extend the office hour from 10 to 11 to 10 to noon. So Monday, 10 a.m. to noon.